This lecture will look at deep neural networks. The main aim of the lecture is to provide an overview. So in this lecture, we're not going to look at the aspects in detail, but we're just going to look at the different aspects that make up deep neural networks and how these different aspects are combined. So the main difference between deep neural networks and the neural networks that we've looked at previously is multiple layers in between your input layer and your output layer. So like in the previous neural networks, we had an input layer and an output layer which produces the activations. We have the same in this case, but there are a number of layers in between. So how does this differ from the multi-layer neural networks that we've previously looked at? So if you look at the multi-layer neural networks, we played with the idea of having one or two hidden layers in that neural network. Now, deep neural networks, as the word deep specifies, there are a number of different layers in between. So this can range up to over hundreds of layers in between. These networks can be feed-forward or recurrent. So some deep neural networks are feed-forward and some DNNs are recurrent. The learning process is basically the same as that in other neural networks. So we start at an input layer and we move from that from this input layer through the multiple layers until we come to the output layer, and at each layer there's learning happening. So the learning is incremental learning, and that involves, as you know from the previous neural networks, is determining the weights, and if there are biases involved, the biases for that layer. Those values then get propagated out through the output layer, and at the output layer the activations of the neural network are determined, and that actually determines what the output of the neural network is. Very similar to the backprop learning algorithm, in deep learning neural networks, the output does not stop at that level. The error in the output compared to the target values of the data instances are calculated, and that's then propagated back through the neural network, as was done in the backpropagation learning algorithm. And like I mentioned, in this lecture, we're going to look at the different aspects that make up deep learning neural networks. You'll see some of the things are very similar, but different terms are used in this context. And the one thing I'd like to bring to your attention is a lot of the aspects that exist for deep learning neural networks. There are libraries available in which you can actually implement to use these different aspects. So things like different activation functions, different optimizers, different loss functions. You can use existing Python libraries for that. So in this lecture, we'll look at an overview, but when we look at the different networks next week, we'll look at how you can implement them in a language like Python using the libraries that are available. So if you want to assess the performance of these networks, how do we do that? Previously, remember we spoke about accuracy, and accuracy looks at how good that particular neural network is classifying. A second measure that's used when it comes to deep learning neural networks is loss. Now, what the loss actually works out is the difference between the target output values and the activations that are being produced by the neural network. And to calculate that loss, different types of loss functions can be used, and we'll look at some of these in this lecture. So these are the two measures that if you see any paper or any work reporting on the performance of deep neural networks, these are the two measures that they're commonly reported on in terms of their performance. There are other measures that can be used like precision or ROC curves, but these are the ones that are popularly used. So if you're actually reporting on the performance of a deep neural network, these should be at least the two measures that you actually report on when you're discussing the performance. So deep neural networks have been used for various domains, but the two in which they've made a major contribution, the one is image processing. Here, the application of DNNs have proven to be even more successful than the human recognition of images in some cases, especially in medicine. And speech recognition is the other area that it's made a major contribution in. A lot of these networks have been employed for natural language processing. So just to re-look at the learning process and the steps involved in the learning process. So the main emphasis here is that learning is incremental. So the network is built layer by layer, and the learning happens in an incremental fashion as the layers are added on. As we've done with all our other neural networks, usually the weights are calculated in a feed-forward manner from the input layer through to the output layer. When the output layer is reached, the difference between the activations that the neural network is producing and the target values in the training instances, that is calculated, and a loss function is actually applied to those values to work out the error in the activation. Now that error is propagated back through the neural network, and it's used to update the weights in an attempt to reduce that loss or to reduce that error. Different algorithms are used to update the weights, and we call these algorithms optimizers. The backpropagation is one of those algorithms that are used. We're going to have a brief overview of these different algorithms in this lecture. But before we do that, we're going to quickly look at some loss functions that have been used. What is very interesting is that the loss function is application dependent. So for different types of applications, different loss functions have proven to be effective. So if you look at regression, the typical loss functions that are used are things like mean squared error, mean squared logarithmic error, mean absolution error. So the mean squared error is the most popular error that's used. Binary classification, binary cross entropy, hinge loss, squared hinge loss. And then interestingly, if you use multi-class classifiers, the binary classifier loss functions are not as effective, and for that reason there's a different set of functions, and these functions that are typically used are things like multi-class cross entropy, sparse multi-class cross entropy, Kullback-Leibler divergence, and those are the popular ones that are used. So once the error or loss is calculated, this value is then propagated back from the output layer through to the layer before the input layer, and the weights are updated in an attempt to reduce the loss or the error. The algorithm used to actually update those weights is referred to as an optimizer. There are a number of different optimizers that can be used. One of the most popular ones is the backpropagation algorithm, which works basically in the same way as the backpropagation learning algorithm. If the backpropagation algorithm is used, then the loss function must be differentiable. If you remember from the algorithm, when it updates the weights or the error, it calculates the derivative, and that is why the function needs to be differentiable. Other optimizers that are commonly used are gradient descent, stochastic gradient descent, mini-batch gradient descent, momentum, add a grade optimizer, add a delta optimizer. Adam is one of the most efficient optimizers that can be used. It's also one of the quickest optimizers in terms of implementation time. RMS prop, Nesterov accelerated gradient. Now, a number of these optimizers, the equations that are used to update the weights will have some type of learning rate, and that's called alpha. From our previous experience with learning rates, we know that this is a parameter and it's a value that actually has to be set depending on the particular problem domain. Different values will be appropriate. So just to quickly visualize where we're at in terms of the learning process, you started off at the input layer, you've calculated weights up until the output layer. At the output layer, you've calculated the loss or error using the loss function, and that's been propagated back, and your weights have been updated. So at each level, if you remember from the previous ways we did training and the previous ways we worked at activations, normally we calculate a weighted sum, and that weighted sum is then forms input into an activation function, and based on that activation function, that's the activation the neuron actually produces. When it comes to deep learning, there are a number of different activation functions that can be used, and these activation functions can differ from layer to layer. So if we look at some of the activation functions that are commonly used, there's a sigmoid function, the softmax function, the hyperbolic tangent function, the rectified linear unit function, a leaky version of this, and more recently the swish function. So we've looked at how the deep neural networks learn. We've also looked at the different types of loss functions that can be used. We've looked at the different types of activation functions. What we're going to look at next are the different types of neural networks. We're going to take one or two of these neural networks and look at them in detail in the module, and also look at libraries that can be used to actually construct them and apply them to different applications. So the most popular deep neural network is the convolutional neural network. This has proven to be really good when it comes to computer vision and image processing, and it's one of the categories of deep neural networks that we're going to look at. Autoencoders are good at performing unsupervised learning, and if we have some time, we'll look at those as well. We then have the restricted Boltzmann machines, and then deep belief networks. Another popular network is a recurrent deep learning neural network called LSTM, which stands for long short-term memory, and it's proven to be very effective when it comes to things like financial forecasting. So one of the challenges that's experienced with neural networks, specifically deep neural networks, is the whole idea of overfitting. And because we know that this is a problem with deep neural networks, we need to be proactive and think of ways in which we can actually try and prevent this. There's been a number of techniques that researchers have come up with that can be used to prevent overfitting in DNNs. So firstly, what do we mean by overfitting? So overfitting is the case where you have your neural network performing very well on the training set, so it has a very high accuracy, it has a very low loss function, but when you then take it and apply that same neural network to your test set, it doesn't perform as well. You get low accuracies. And this is what we mean by overfitting. So different ways in which overfitting can be overcome. The one is reducing the size of the neural network. So the idea here is the bigger the neural network is, it overlearns, and therefore it's overfitting. Another technique used to reduce overfitting is the idea of regularization. L2 regularization is a very popular technique used to prevent overfitting. There's also the idea of early stopping, so stopping your algorithm before it converges. And then adding dropout, where you take out certain components at different levels in your neural network, especially at the output level. Another very interesting idea when it comes to deep neural networks is the whole idea of pre-trained neural networks, or pre-trained models, linked to transfer learning. So why do we need this? We know from the work we've done so far with neural networks that in order for your neural network to generalize well, it needs a lot of data. Especially if you're doing things like image processing or speech recognition, it needs to be trained sufficiently. But for a number of domains, it's not always easy to find data. I mean, we're working with two problems, one in veterinary science and one in architecture, where the training sets available in terms of the different images available are very small, and it's not sufficient for the neural network to learn on. So the smaller your data sets, the lower your accuracy rate is going to be. So one way of overcoming this is the whole idea of transfer learning. And with transfer learning, a neural network, a pre-trained neural network, is trained on a different data set that has, for example, images in it, but it's a very similar area, not exactly the same. And then that neural network is reused in some way for the new training or the new problem domain that's similar but does not have enough data available. So you can guess that if you use the neural network as is, it's not going to generalize well because it was trained on another set of data. But what we do is we keep certain aspects of that neural network the same, and we change other aspects. So the things that are normally reused are things like the features of the neural network for that particular layer, or the weights for the neural network. So one common technique used for transfer learning, there's different techniques for transfer learning. We're not going to go into those techniques in detail. The main aim of this is that you just need to know that this is available, it's an option, and it can be quite powerful, especially if you don't have sufficient data. So the one technique that's used is the pre-trained neural network is left as is, but only the last layer is retrained. Another option is selecting different layers to retrain. So you can leave some layers as is in terms of features and weights, and you can retrain other layers. So pre-trained models exist, and you can actually use libraries that have these pre-trained models. Python has a number of pre-trained models. When it comes to image processing, a library that these models are commonly pre-trained on is something called ImageNet. So ImageNet contains a number of or thousands of images, and there's usually always some related set of images that you can find related to the problem that you're working on, and you can pre-train that model, and you can use the existing libraries to do that. So some examples, what we're now going to look at are some examples of pre-trained models that exist that can be used for different domains. So the models that are pre-trained, they are trained specifically for a particular application. So there's a set of models that can be used for computer vision or image processing, and there's a set of models that can be used, for example, for natural language processing. So if we look at computer vision, the common the models that exist that are pre-trained that are commonly used, VGG16 is a very, very popular pre-trained model that's used for image processing. It's very effective. VGG19, Inception V3, Exception, and another very good model is ResNet50 that also performs very, very well for image processing. Similar models also exist for natural language processing, so Word2Vec, GloVe, and then lastly FastText. So the purpose of this lecture is just to provide an overview of deep learning and for you to familiarize yourself with the different concepts, also to see how the different concepts are linked up. When it comes to implementing these deep neural networks, there are existing libraries that you can actually use instead of coding from scratch, and you can use these libraries in two ways. So either you can build up a neural network incrementally by adding a layer each time, or alternatively, you can actually use one of the pre-trained neural networks that exist in the library to perform the classification or the regression that you need to perform. So these neural networks can be used for classification. They can also be used for regression. So they're good at estimating functions. They're good at performing both supervised learning and unsupervised learning. So in our next lecture on Tuesday, we're going to take one of these or one of the sets of deep learning neural networks, and that's going to be convolutional neural networks, and we're going to start looking at that in detail. And we'll also see how you can use Python to implement these neural networks given the libraries that are in Python.